Good afternoon. I'm Pat Donovan Potts, the Stormwater Manager with the City of Jacksonville. I'd like to welcome you to the New River Roundtable presentation on climate change in North Carolina. We will have two speakers today, one after another. The first speaker will be Dr. Ryan Boyle. He will present on climate change, and then we'll have a short question and answer period afterwards, followed by Dr. Alex Glass. He will present second on sea level rise in North Carolina. There will also be a question and answer period after that one as well. It will be a little bit longer. These are topics that are very important and could affect us all, not only as citizens, but as the municipality and the county. Having said that, we'll get started, and I'm going to introduce first Dr. Ryan Boyle. He is a North Carolina native from Durham and with an undergraduate and graduate degree from NC State University. As state climatologist, Ryan is the chief scientist with responsibilities to develop and promote the office's climate services for extension, research, and education of applied meteorology and climatology. Ryan supervises staff and students, assists NC State and county agencies, and interacts with a wide range of public and private sector clients to ensure development and delivery of advanced climate science and services. As an applied climatologist, Ryan focuses on how climate data and climate science can be better used to improve monitoring and decision-making for the sectors of our society most sensitive to weather and climate impacts. Ryan has spent much of the past decade working on drought issues with the North Carolina Drought Management Council and is currently working with various climate centers throughout southeastern region. Ryan also holds an appointment as an extension assistant professor in the Department of Marine, Earth, and Atmospheric Sciences. If you will help me, please welcome Mr. Ryan Boyle.
Thank you. Happy to be here. Talk to you a little bit about weather and climate in North Carolina, how we think that might change in the future, some of the basis for how we understand the climate variations and change over long term, and what that might mean for us here in North Carolina. And I think of this as a series of challenges. We deal with all kinds of weather and climate hazards every day. Climate change adds another twist to that, but it really comes down to challenges that we have for how we deal with risk management at the local level for our monitoring programs, for our planning, as well as predicting what might happen into the future. Thanks for the kind introduction. I'm a scientist at NC State University, and the State Climate Office is basically a public service center. We're here to be that statewide resource for weather and climate expertise, especially when it comes to the decision making that is often done at state and local levels. We have, in addition to a series of extension scientists, we have a tremendous amount of climate data at our fingertips. 30-odd terabytes of spinning disks with gobs of climate data right at my fingertips that I can pull down and generate all kinds of information. Sometimes this is as simple as what the record snowfall is in North Carolina for the local bar bet that you might have. Sometimes it's really critical stuff, like you're trying to recruit, for example, a baseball team to the city of Fayetteville, and they're really interested in how often it rains during the evening during baseball game hours. What's the frequency of that? Because that's going to determine the type of location they go to. So there's a lot of climate sensitivities in our economy. They estimate about a third of our total economy is sensitive directly to weather and climate. That's a tremendous amount of investment and potentially a tremendous amount of exposure that we want to make sure that we mitigate and be prepared for. We're located at NC State University, housed on their Centennial campus. Not a state agency. We are a university center and are supported by grants and contracts, just like all the other fine folks at the university system. So I want to start off, when we get into this, drawing the distinction between what we consider global warming versus climate change. So global warming is, what's that? It's the warming of the globe, generally referred to as the increase in global average temperature that's been observed over the past 150 years or so. But that's not climate change. Climate change manifests itself locally. Okay, and we think of climate change as variations not just in temperature, like we think of for global warming, but changes in precipitation patterns, changes in severe weather, changes in all the other factors in the atmosphere that might have connections to global warming, but also have other connections to changes in our land use patterns, changes in our farming and irrigation practices. All of these other things also impact our climate. And we purposefully draw a distinction between global warming and climate change because they do have different meanings in terms of the science. I want to go over a few things real quickly before we get into the impacts to North Carolina. Generally, climate comes down to an energy balance. So I'll cover the energy balance of energy in the atmosphere very briefly, talk about the complex surface of our Earth, and that's what drives changes in heating patterns and changes in our land surface, therefore are going to affect changes in our climate locally over the next year, over the next decade, and over the next century. And then changes to our atmospheric composition, the chemistry of the atmosphere also has an impact on our climate. And then finally, our location on the Earth's surface has a big impact on our climate. And all of those change on different timescales. So let's start off first with energy balance, and in particular the role of clouds, because it's an area of uncertainty that we have. There's a lot of active research going on. See all this different energy that comes down from the sun. Let's see if I can get this pointer to work right here. That doesn't work out so well. Let's try something else. This isn't working at all. How do you get that little thing to come up here? Okay, well, I'm going to give up on that then. So you have energy coming. Oh, that's not supposed to work. So we're having some technical difficulties here. It worked fine when we were practicing earlier. I may need some help from production. I think, did they break something? Did I break something? Okay, that's not working. So I will be pointing with my hand, I guess. I can't point with my hand because I'm stuck behind the microphone. I can't walk. Someone cleared it. Thank you. So what you have here is energy coming from the sun, okay, and a lot of that gets absorbed by the Earth's surface and then gets re-radiated out as heat that heats the atmosphere. So you want to go home and play a little trick on your neighbor and ask him a silly question like, what heats the air? It's not the sun. It's the Earth that heats the air. Most of the heat energy from the sun passes directly through the atmosphere and hits the land surface. So when it hits the land, the ocean, a blacktop surface, a grassy field, that's when it converts from that light energy into heat. And so if you have lots of blacktop surface, the air gets hotter. If you have ice, a lot of that gets reflected out, it stays cooler. So depending on whether you have mega cities with lots of asphalt or you have nice well-irrigated fields, you get a very different temperature result. You can do this, going out today when you step outside. The street feels hotter because it's a black asphalt surface. You go over into the field nearby, it's going to be quite a bit cooler walking on it. So that happens, that impacts our climate locally as well as aggregates up to affect it regionally and even globally. The other trick here is some of that energy that does go back out into the atmosphere gets absorbed. And so there's greenhouse gases that get a lot of the attention, but there are other factors that also absorb energy in the atmosphere that serve to trap a lot of that heat in the lower part of the atmosphere. We think of clouds as being one of the big factors. And we found that if you have lots of big poofy clouds, the kinds that you see on a fair day, those actually can reflect a lot of energy back out to space. But when we have thin, high-level clouds, cirrus clouds that we typically see around here in the humid summertime, those actually act as a blanket and can keep more heat near the surface. So one of the challenges we have as climate scientists is trying to predict what kind of cloud regime we're going to have into the future, because that's going to impact the kind of temperatures that we experience locally as well as globally. And then, of course, our location on Earth is a big factor as well. We sit right at the nexus of three major air masses and some really complex topography. So the highest mountains in the eastern U.S. are on our western doorstep. They wreak havoc with storm systems that generally come from the west. We have large warm air masses that come up from the Gulf of Mexico and from the Caribbean and the tropical Atlantic Ocean. And those bring us a lot of those warm, very moist conditions that we experience in the summertime. So if you take away, for example, the Gulf of Mexico, we would look like a desert. In fact, if you look at our latitude all around the Earth, what you typically see mostly is deserts, with two major exceptions: the southeastern United States and the Indian subcontinent, where at that same latitude, about 33 degrees north, you have a very warm ocean to the south. If you take away that ocean, we look much more like the desert Southwest. We look much more like the Sahara Desert, which are also at our same latitude. So the presence of those oceans is what brings us the hot, sticky summer weather that we get. It also is what brings us the tremendous agricultural productivity that we have in the summertime, the regular routine rainfalls that certainly we're very well of this year with a very wet June and July this year. So changes in our latitude, which happen over eons due to geological forcings, would impact our climate. Changes in the oceans as they cool and warm, also impact our climate. So these are things that we also want to be aware of. It's not just what happens in terms of cloud cover. It's not just what happens in terms of chemistry. It's not just what happens in terms of our land use. But changes in the ocean have a direct connection to the climate that we experience here in North Carolina. And because of all those complexities, we have one of the most complex climates in the United States. In fact, we easily have the most complex climate in the eastern U.S. You have to go really to California to get the same types of complexity that we have here because of those warm bodies of water, because we're far enough north that we get plenty of cold air, especially in the wintertime. We're far enough south that we get lots of warm, moist air throughout the summer, but even in the winter. In fact, on any given weekend in January, it's very likely that we'll have temperatures here in the 70s. And that's not unusual, actually. Going back over the data records, that's quite common. In fact, it's very uncommon if we don't have temperatures here in the 70s for at least a couple days in January. What this means is that we have tremendous amount of variability in our climate, and all of these, well, from my standpoint, very wonderful things to study about our climate. We get every kind of severe weather here. You name it, we get it. Ice, floods, droughts, snow, heat waves. We get it all here. It makes a great place to study weather. It also means, however, that our society is exposed to some of these things that we considered hazards. And so we want to be aware of those hazards, the frequency at which they occur, so that we can take appropriate risk management steps to basically alleviate some of those concerns for the long term. So we're going to talk about variations in our climate, what drives it. I want to focus on short-term variations in our climate first, what happens season to season. And then we'll talk about longer-term variations in climate, what happens to changes in our atmospheric composition, what happens to changes in our land surface, because these are things that do happen over the course of a lifetime. We're going to throw out the geological issues, plate tectonics and stuff like that, because that's not going to happen in any of our lifetimes. Those are things that happen over the order of eons. So let's talk about seasonal variations. And to do this, we need to talk a little bit about the jet stream, because the jet stream is what brings us a lot of our winter weather patterns. The jet stream is associated with storm tracks, especially in the wintertime. And in any given winter, we're likely to have a jet stream that typically dives deep. It pulls up lots of moisture from the Gulf of Mexico, and we get lots of coastal storms. We get lots of widespread snow sometimes, especially in western North Carolina, but even here, snow is not unusual. However, we do understand that there are some things that cause shifts in those patterns. For example, in the tropical Pacific Ocean, so we watch this area here, and when it's cooler than normal, we call that a La Nina. When it's warmer than normal, we call it an El Nino event. And when we have La Nina patterns in the tropical Pacific Ocean, we're much more likely to see that jet stream retreated further north. And what that means is fewer storms that dive deep into the Gulf of Mexico, fewer storms that come along the eastern parts of the Appalachians, and what we see is drier conditions across the southeastern U.S., wetter conditions across the Ohio River Valley. This is actually a big deal for us because we can predict this 6 months in advance now. For the most part, we know whether our winter is going to be wet or dry, usually by this time of year. And that's a real boon, especially if you have sensitivities to wintertime precipitation. So for example, a lot of our groundwater recharge occurs during the wintertime. We have little evaporation, but we have a lot of regular rainfall that comes in. If we're going to have a dry winter, we're much more likely to start with our reservoirs low, start with our groundwater supplies low, much more likely to move into a drought if we have a La Nina winter. Now, in the summer, we also have variations, and this is what most people tend to think of as associated with drought in the summertime. On any given year, we're dominated by our Bermuda high pressure system. Now notice there's no jet stream on here. The jet stream is actually retreated much further north in the summertime. We don't generally get much impact from the jet stream and from cold fronts in the summertime, and if we do, they're pretty weak. But very much influenced by what happens with this tropical Bermuda high pressure. We call it the Bermuda high because it sits over, well, Bermuda, right? And what that means is winds around a high pressure system are clockwise. We get lots of warm, moist air blowing up from the Gulf of Mexico, from the Caribbean and tropical Atlantic. Sometimes, like in 2007, that high pressure system elongates or shifts. And if it shifts closer into land or over the southeastern states, what we get is a shift in the wind patterns. And instead of having warm, moist air blowing up over the southeast, it blows up over parts of Louisiana, Texas. In 2007, they had quite a bit of flooding in those parts of Texas. And what we have coming into North Carolina is a continental air mass. There's not a large body of water up here. It's not warm. It's dry. And so our droughts tend to be associated with very heavy, or excuse me, a very strong high pressure system, very strong subsidence in the atmosphere, sinking air, and not a lot of rainfall. The problem is we can't really predict this 6 months in advance. In fact, we're doing good to predict this 6 days in advance. That's one of the limitations. We understand after the fact why we have droughts in the summertime, but we can't yet predict it. Now, longer term, changes in our climate and the variations in our climate have to do with a lot of other factors beyond changes in the high pressure systems, changes in the jet stream. Those are shorter term patterns that affect us season by season. Longer term changes, things that happen over decades, that happen over centuries, that happen over millennia, have to do with changes in our atmospheric chemistry, the composition of the atmosphere, the gases that and the particles that are in our atmosphere that impact how much radiation comes in and then what happens to it, how much goes back into space, how much gets absorbed. We're really grateful. We talk a lot about greenhouse gases. We're actually quite grateful that we have greenhouse gases. It'd be 60 plus degrees cooler on the surface of the Earth if we didn't have all those greenhouse gases. So we know that they warm our atmosphere. The other thing that we're concerned about, of course, is then longer term changes in those greenhouse gas compositions. The ones that we put up there by burning fossil fuels is one of them. We also have the concerns of changes in water vapor over time that are also going to amplify that. Now, you don't hear water vapor getting a whole lot of attention in the news media because water vapor cycles through the atmosphere on the order of days. They can do tracers in the models, they can trace it in observations. They see that water vapor moves through about 4 to 6 days. So it gets evaporated up and it precipitates back down. The other greenhouse gases that get a lot of attention are ones that stay up in the atmosphere for 50, 100, 150 years or longer. And that's why things that we're releasing now are going to continue to be up there and will continue to impact our atmospheric chemistry for decades. I've mentioned already the changes in cloud types and the amounts of cloud cover. That's something that we concern ourselves with, and that's something there's a lot of active research because we don't fully understand exactly whether or not we're going to get lots of high poofy clouds that reflect a lot more energy, or if we're going to get a lot more high cirrus clouds that act as a blanket on our atmosphere. And then finally, changes in our land surface and the ocean. So when we say land surface, we're talking about our land use changes, how our cities grow and develop. Those impact our local climate. Our vegetation changes. Those impact our local climate. I'll choose some examples here. Certainly, we see this very strongly in a lot of the urban areas across the U.S. We don't get as cold as we used to. Our maximum temperatures in some cases have been rising, but even in the southeast where we haven't seen as much warming, our urban areas have been getting warmer. And as soon as you go outside of the urban areas into the rural areas, you don't see that same signal. And that's because we've put a lot more asphalt, we've put a lot more energy, we've changed the land surface of our cities, and those absorb more radiation, more heat energy, and they keep those areas warmer. In reality, it's not that the high temperatures are that much higher, but the low temperatures have been really increasing. So we don't get as cold as much in the urban areas. Second, vegetation. If you looked all around this area 100 years ago, you wouldn't see any of these trees. It was all non-irrigated farmland. We started reforesting the southeast really starting in the 1930s, 1940s, and since then. So we've had a tremendous regrowth of the forests in the southeastern United States over the past 50, 60, 70 years. And what that's done is changed the reflective nature of the Earth's surface. We actually pull a lot more moisture out of the soil because of those. It transpires year round. And what we see then is a cooling effect from a lot of the forests. Again, it's a human-made climate change. We chose to cut the trees down. We chose to grow them back. We choose how we use the land surface. And it impacts our climate locally. And then finally, ice cover. It's something that doesn't affect us here in North Carolina. We don't have a whole lot of ice cover. If we do, it lasts a couple days, and it's a big nuisance and causes power outages. Here we're talking about ice cover in the Arctic and the Antarctic. And those changes over long term also impact us. And it's quite interesting. For example, we hear a lot about the loss of sea ice in the Arctic area, and that may actually shift the weather patterns that we experience here in North Carolina. So if in the early fall it takes longer for the Arctic to freeze back over, that means that cold air that develops over Canada develops further south over Canada. It may mean it allows us to dip possibly further south into North Carolina. So there's been some really interesting studies that suggest that some of the cold weather that we may be experiencing here in recent years in November and December, unusually cold weather, may be associated with the warming of the Arctic because that continental air mass that forms over Canada would otherwise form further north. There's a lot of connections here that we don't fully understand, but these are the things we're trying to study and learn more about. And it's important to cover how we monitor and detect these things, because it's not a bunch of hand waving. There's a lot of very advanced technology. There's a tremendous amount of data that's being explored on any given day. We use satellites, but satellites really only go back about 30 years for giving good global coverage. You've got to go back to the, late 1970s, early 1980s to get good satellite coverage of the global surface temperature, global ice coverage, some of those factors. Going back further, going back 100, 150 years, we have surface temperature. So you have a thermometer at your house. It's probably an alcohol thermometer. You might even have an old mercury thermometer. But for generations, that's how we measured temperature, day by day, by volunteers all around the nation and the world. But climate change happens over more than just 30 years, and it happens over more than even 100 years. It happens over many hundred years and millennia. So to go back even further, we have to use proxies, things that are closely connected to changes in temperature, but that don't directly measure the changes in temperature. So we use tree rings, we use ice cores, and we use soil sediment cores to estimate with pretty good accuracy what temperatures and atmospheric chemistry has been like. Going back now, they can go back 800,000 years. It's really amazing what they've been able to get, especially out of the ice cores. And that's when we combine all these together, this help us understand the breadth of our scientific knowledge on climate variations and change over different timescales. Short-term things happen day to day, that happen season to season. We can't capture those in ice ring and ice cores and tree rings. Those are things that really only tell us what's happening on a year-by-year basis. So for that kind of variations, we really have to have sensors that are out there that are measuring on any given day. So let's come to North Carolina and what the global change means here in North Carolina. So what you have up here on the plot is the annual temperature for the globe since 1895. And what you see on there is some variations around a linear fit. I'm not a huge fan of linear fits, but it gives you the sort of sense as to what the background trend is, right? And what you see are the year-to-year variations in global average temperature. Some years are up, some years are down. Overall, it's been increasing. This is a statistically significant change, which means that the trend dominates the background noise. Okay, so the signal-to-noise ratio is much higher. It means it's a meaningful trend. It's not just that we're making stuff up. We actually have a meaningful, statistically significant trend, and we can test this scientifically, and it has validity. This is the North Carolina temperature pattern over that same period, overlaid again with the global temperature averages. And what you see on there first is that North Carolina's temperature varies a lot more from year to year. Tremendous variability. As you aggregate up from North Carolina to a region, to a nation, to a globe, you dampen out a lot of that variability. But here locally, where we care about these things, the variability is tremendous. How about those trends? Well, the trend in North Carolina is flat. Since we have statewide records going back to 1895, there's been no real warming. Does that mean there's no global warming? There's no climate change? No. It means there are other factors here locally that also dictate what our climate is like, and it's important to understand those. It's also important to point out some interesting patterns here. So for example, since the mid-1970s, we've been warming quite a bit. This happens to be when the satellite record began. But it may not be unprecedented compared to what we experienced in the teens, 20s, 30s, and 40s at the turn of the 20th century. So things that we experienced back in the teens, 20s, and 30s may be relevant to the things we're experiencing now. We don't have the same rich nature of the impacts of our climate from back then that we have now. We don't have all that data. But when we look back through the newspaper articles and we talk about the bad drought years of 1925, in many ways, things are much better now. We didn't have all those trees back then to keep things cooler. We didn't have all the reservoirs that we have now for providing for our water supply and make us much more resilient to drought. But the long-term change in North Carolina and the broader Southeast is actually not nearly as strong as the global average. And in general, as you go further north towards the Arctic area, the warming increases quite a bit. The amount of warming that you see in the northern states, in Canada, in the Arctic area is tremendous. But the Southeast is one of those areas, perhaps because of the reforestation of the Southeast over the past 100 years, that hasn't seen as much of the warming. Precipitation is even more variable. There's a slight increase over that trend, but it is not statistically significant. So what it means here is that there's a trend, but it's not meaningful given the year-to-year variability. And what you see is lots of wet and lots of dry. And that's North Carolina. We experienced drought in the past, we will experience droughts again in the future. We've experienced floods in the past, and we will experience floods again in the future. What we're most concerned with is, are those frequencies or intensities going to change? And that's where we spend a lot of our time trying to study, trying to piece together from models to give us guidance as to what we might expect in the future. Unfortunately, the global models that we use are designed to handle things globally. We have to do a lot more advanced technology and science to really predict what's going to happen locally. There's a lot more work that needs to be done. But that temperature and precipitation record, especially over the past 100 years, we can put that in a context for, say, the past 2,000 years. So these are tree ring-based estimates of rainfall during the springtime over the past 2,000 years. And what you see are tremendous periods of wet and dry. And what I put on there in that dashed red line at the bottom, this is the drought of record from the past 100 years. And what you see are numerous examples where droughts were more severe than anything we've experienced in the past 100 years. So certainly if it's happened in the past, it can happen again in the future. How do we predict? We use models. We use models to predict weather. We use models to predict seasonal changes as well as longer term changes. Weather models are what you're used to seeing every night on the evening news. Cold fronts, storm systems, how they vary from hour to hour, day to day. We can also extend those out over the next season. And using things like a relationship to El Nino and La Nina, we can give meaningful projections for what the wintertime precipitation pattern is likely to be over the continental U.S. These are very good, fairly meaningful projections for most people, but not all. It depends on what the decision horizon is for your need. If you don't have any decisions that are being made on seasonal timescales, you probably could care less about this. But we're used to making decisions on a day-by-day basis. What to wear, when to plant, when to harvest, when to irrigate, when to go to the beach. These are things that we are used to emphasizing, and that's why so much of our research dollars have gone to improving weather forecasting over the past 30 years. With climate, it's a little more complex. Actually, it's a lot more complex, because we have to predict not only where those cold fronts are likely to go, but we also have to predict how the oceans are going to shift. We have to predict how the land surface is going to shift. We're going to have to predict how the atmospheric chemistry is going to shift. We're going to have to predict how people are going to change. And folks, the physics of the atmosphere is really easy. People are really tough. So my job, relatively speaking, is easy. The social scientists, the people who study how humans make decisions, how people will evolve, that's much more complicated. But here's what we think is likely to happen. There are three different ways that we expect the climate to shift. One is, if here we've got a distribution of temperatures where you have a few cold events, a lot of weather, temperatures right in the middle, and then a few really hot. So this is the probability or the number of events that occur, and this is how they range across the temperature spectrum. If you just had a shift in the mean, in the averages, a broad averaging of the global warming, you would expect to see fewer cold, more hot, a general shift of the entire number of events towards the warm side. But you can also have a shift in the variability. So in this case, what you get is more cold and more hot. What we think is more likely to happen is a combination of both. A shift in the mean towards the warm side, so that you'll have about the same amount of cold, but more hot. This right now is the most likely scenario we see happening globally. How does that manifest itself locally? Well, we use global models to predict how global things are going to happen, but global models aren't really useful for predicting what happens here. It's kind of like using a model of how all of the automobiles in the United States, their fuel efficiency, to predict exactly what your car's fuel efficiency is going to be on any given day. You wouldn't look at EPA standards for all motor fleet vehicle efficiencies to predict exactly what your car is going to do on any given day. Similarly, we don't use the global models to predict what's going to happen here in Jacksonville or even North Carolina over the next century. We have to use other tools. We have to use more advanced tools. We have to use a lot of impressive computing to downscale these global processes to capture the weather and climate that most impacts us on any given day. And the computing just isn't there yet to do it. We're probably 15, 20 years from the computing to be able to predict with the accuracy that we have now in weather models to predict that same for our climate models. Because climate models are much more complex. Weather models are basically not that much different from where they were in the late 1970s. They have higher resolution, they're a lot faster, but climate models have added a lot more in terms of dealing with sea ice, aerosols in the atmosphere, sea spray, biogeochemical cycles, carbon cycles, ice sheets, marine ecosystems, atmospheric chemistry, all these things now have to be captured in climate models that in weather models we don't care about. We could ignore all that stuff because it doesn't change on a day-to-day basis. So you have to capture all those things into climate models. And the climate models then can go through a range of different manipulations to be able to predict what might happen locally. And there are dozens of them out there. The IPCC uses 30-odd different models to give them global guidance. We can downscale those to try and get meaningful local guidance. And here's a range of some of the different solutions here. This is looking at temperature for specific latitude and longitude. I believe this is in western North Carolina going over the next 100 years. On any given one of these, I promise you is not correct. None of these models is exactly right. But they're useful for giving us the direction in which they go. And they all show warming. Some of them warm faster than others. Some of them have more jumps and spurts in them. But they all show us generally getting warmer. And because these models collectively can replicate what has happened in the past 100 years, we have some confidence that they're useful for the future. So, in terms of what we experience, in terms of our hazards that we face in North Carolina, what does all this mean? Well, we experience almost every kind of hazard here. And so shifts in those hazards, the frequency and the intensity, is a big deal for us. And of course, we have a tremendous amount of our economy, of our society that is exposed to these hazards on any given year. So what I'm going to do is go through these broadly and then season by season to give you a sense as to where it's going. This is a report. These are figures that are taken out of a recent report on the National Climate Assessment that I don't want you to look at any of the lines, maybe blur your eyes a little bit, because even these are not precise numbers, but they give you a sense as to where the trend is. And what you see is that overall, it's likely to warm in terms of our temperatures. These are increases 2041 to 2070 minus a reference period of 1971 to 2000. And what you see in particular is it suggests that the summer conditions in the Carolinas are going to where you feel most of it. So our summers are likely to be warmer overall. We're especially seeing this in our minimum temperatures. It is not getting as cold in the summer as it used to. Precipitation-wise, there's a lot more uncertainty here, but in general, what you see is things are probably about to stay the same or maybe get a little bit wetter. The exception to this is summertime, where it's expected to be some drying here across the more western states. Here in the Carolinas, we still think we're likely to be a little bit wetter. So what is a winter going to look like in North Carolina? Based on the projections we have, based on the historical analysis of the data that we have, we're probably going to have more days where it's warm, more of those 70-degree days in January. We're going to have fewer days where it gets really cold, fewer of those days where it doesn't get above freezing. But we're still going to have cold days, and we're still going to have warm days. It's not like we're going to suddenly go and never have another freezing day. We're not going to suddenly have another day with no snow. Now, we have to have all the right set of conditions to get snow here anyway, but it will still happen. It may not happen quite as frequently, but when it does happen, it can still shut a town down. But if you're in an area now that, for example, is looking at, do we really need to invest in a long-term contract for road salt and road spray? Maybe that's something where if you're looking at a 10-year contract, maybe you want to rethink that. Maybe you don't want to invest in that contract now because it may not pay off. We will still have snow. The frequency of snow will probably change a little bit, and we'll probably see plenty of snow still at the higher elevations, but those areas that are marginal now, Jacksonville, Raleigh, Charlotte, probably won't see as many days with snow 100 years from now than they've experienced over the past 20 years. So this is how you see the change in the temperatures here. Where you see those hashed lines in the temperature diagram, those are statistically significant trends. So they're meaningful. It means more of the models agree than disagree here. So we're not going to get as cold. We're going to see a big shift in the number of days where it doesn't get below 32 degrees. What's the spring going to look like? Spring is a transition period, just like fall. Any given day in March, it could be freezing cold or it could be spring-like. That's not likely to change a whole lot. What we'll probably see is a shift towards more of those warm days a bit earlier, but we may still have a big freeze event that comes through in April that would otherwise be normally timed. One of the concerns for agriculture, of course, is if you have, for example, perennial fruits, blueberries, grapes, you're going to emerge much earlier, and then you're more susceptible to those spring freezes. That's a big deal if you're trying to grow those fruits. Thunderstorms are one of those things that we don't get the giant thunderstorms that they get out in the high plains. We don't think that's going to change. But there's nothing right now to suggest they're going to get weaker. In fact, a few of the studies that have come out suggest that they're more likely to be stronger thunderstorms. Tornadoes, we don't know about. Again, we don't get a lot of tornadoes here, and while they do impact us, it's very rare for us to get the big F3 or stronger tornadoes. We've never had an F5 in North Carolina. We don't think right now, we don't have evidence right now to suggest we're going to see a big shift and suddenly start having F4 and a lot of F5 tornadoes. We get lots of hail. We may continue to get more of that hail as we see more of an intensification, and perhaps in the updraft speeds, you may get more hail. There's some uncertainty there. And so we don't feel real confident in making meaningful predictions yet in those severe weather categories. Summer, it's going to get hotter. That's just the way it is. And in particular, what we're going to see is probably more summers where it doesn't get as cold at night. We've been seeing this not just, especially in the urban areas, but we're seeing this in a few rural areas as well. The trends in minimum temperatures overnight are increasing. That's a big indicator not just of land use changes, but of the background climate signal as well. So we may not cool off as much at night, and that's important for human health because a lot of people, if they don't have air conditioning, and there are still folks that are out there that don't, if you don't cool off enough at night, you don't get that recovery that you need from the daytime heating. When it rains, there's suggestions now that when it rains, it's going to rain more heavily, but we may actually have fewer days with rainfall. Now, that may mean more drought if you go a long enough period without that rainfall, and then when that big rain does come through, it may have implications for storm run or runoff. So all that stuff that gets dried on the roads, then a big flushing rain comes and flushes all that down into our rivers, that has implications for our water quality and our drinking water safety. So here's some more maps to show you the shift in the number of days with temperatures above 95 degrees. Again, statistically significant trends here. Increases in central North Carolina of 20 days a year with temperatures above 95 degrees and then 3 decades from now. It's already pretty miserable here in the summer times sometimes, and so I don't think anyone's really looking forward to more 95-degree days. Again, blur your eyes a little bit. I don't know if this orange that's down here in South Carolina is going to creep up into North Carolina or not. That's not really the point. The trend is it's going to get warmer. Autumns, we probably won't see more frequent hurricanes, but there's been a lot of scientific study recently to suggest that we're going to see more intense hurricanes when they get formed. That right now we have a lot of hurricanes that form in fairly marginal conditions, and those conditions are going to become even more marginal in the future as we have more events where Saharan dust comes out into the tropical Atlantic when we have less stability in the atmosphere. But when those storms can get organized and they form and can get the rotation going so they can sustain themselves, they're going to have much warmer oceans, and that's going to mean more intense hurricanes. So more Category 3, Category 4, Category 5 hurricanes, the ones that cause widespread damage. Now, of course, even a tropical storm can produce widespread damage here in North Carolina. Remember, Hurricane Floyd made landfall as a tropical storm. So for us, the big factor is rain, and slow-moving storms have a bigger impact on us than fast-moving storms, even if they are a strong Category 3. We'll probably also see is a later first frost. Now, this may actually be a benefit for some growers. It may actually extend the growing season. So the concerns that folks have right now about not getting their soybeans in the field in time after their winter wheat harvest may be alleviated. They may be able to grow that crop a little bit longer to get a little more energy in and have a successful crop. Okay, so you've heard me say a lot of things about, well, we might see this and we may see this, and we don't have a whole lot of confidence in this. So who cares? A lot of these are risks that we already know how to deal with. We know how to deal with hurricanes. It's not like we're going to suddenly get a new hazard that we've never experienced before. And so while I'm not a policy expert and don't pretend to purport policy, things that we've experienced in the past that we know how to deal with, taking those steps to make ourselves more resilient is going to help us a lot into the future. Because if we've seen it in the past, we're going to see it in the future. And it may be a little worse with climate change. What do we do about it? We have all these vulnerabilities. We have science that can inform our policy making, but science doesn't dictate policy, it just informs it. There are a lot of other reasons that go into any given policy decision. Hopefully, science is influencing it appropriately. But ultimately, these policies are made by we as humans, and they involve a lot of different factors. So we're hoping that meaningful climate science and all the wealth of data that we have can inform those policies in a meaningful way. And with that, my contact information, and I guess I talked a little too long, so we may not have as much time for questions. You're not allowed to talk unless you have the microphone.
Do we have any questions? Yes?
In the meantime, they could come up here and use
Test.
this one. Oh,
Test, got
you
it.
Got it.
Okay, do we have any questions? Yes, no? He did a thorough job, didn't he? Well, thank you. We'll bring him back up again at the end of Alex's presentation as well. So thank you, Ryan. So all the climate change, what does that mean to sea level? Our next presenter is Dr. Alexander Glass. He is a lecturer and a director of undergraduate studies in earth and ocean sciences in the Nicholas School of Environment at Duke University, where he teaches courses in geology, oceanography, paleontology, and climate change. He received his PhD from the University of Illinois in geology and paleontology. Although active as a paleontologist, his primary passion is science education and the study of pseudoscientific movements. As an educator, he regularly speaks to audiences about biological evolution, climate change, sea level rise, the interaction of science and religion, and the nature of science. Alex lives in Chapel Hill with his wife, Jennifer, who's also a geologist, and his two sons, Adam and Kyle. Please help me welcome Alex.
Thank you. Can I have this, is this turned on, this mic?
Yes. Yes.
Hello? Can you hear me?
Yes.
Can you hear me? Excellent. I kind of like to tend to move around a little bit, so. First thing I want to say is that I'm here as an educator today. My specialty in science is paleontology and geology. My passion lies in science education. And one of the things that I'm very interested in is about how people perceive science and the nature of science. It turns out that there is a huge diversity of views out there, especially among the public, including within the scientific community, about what science is and what it isn't, and where the boundaries lie between pseudoscience and good science. There's quite a bit of disagreement on this, particularly in the public sphere, and so I'm very interested in people's perception. So I come to you as an educator today to tell you a little bit about sea level rise, which, as you all know, has been somewhat controversial in North Carolina. I may understate that. But I'm going to give you just sort of a basic introduction as to what we know about sea level rise, and then we can go to questions afterwards. So first of all, I want to mention Oren Pilkey unfortunately could not be here today because he is actually in Ireland. He took his granddaughter to Ireland to go to college. So he will not be here today, but he said he is here in spirit. So the first thing I want to talk about is, as a geologist, of course, what better place to start a talk than in the midst of some beautiful geological setting. This is the Badwater Basin in Death Valley. And notice there's something interesting here. It says on the sign that this is at 282 feet below sea level. And this is sort of, I find in my experience, for those of us who don't live near the coast, and much of America does not, when they come to places like this and they will go up on mountains, this is the first time they are really actually exposed to the idea of sea level. Okay, well, we measure clearly sea level must be some static number that's 0, and then we measure everything up from that. And in this case, we're actually 282 feet below it. And that's really unusual because if this valley would be actually attached to the ocean instead of draining into the ocean would actually drain into this valley. Luckily, it is not attached to the ocean, and so that's not what happens. So this is one of the lowest places in North America. And by the way, a thing on accuracy, this image is from the US Metric Association, and if you're paying very close attention, you're looking very carefully at my numbers, which I'm sure you are, you'll know that 282 feet is not 85.5 meters. It is actually 85.95 meters. So now you get an idea what the accuracy level of my talk, okay, plus or minus whatever that percentage would be. So the first thing I want to dispel is a myth, and that is that sea level is level. It is not. It is one of probably the worst misnomers in scientific history that we call sea level, or that it's a level. I want to thank Glenda McDonald here for providing me with this picture from her blog. It's incredibly difficult to find a photograph of very still seas. Most of the pictures there you take are lake beds, and they're very still, and I don't even want to show you a lake bed. This is actually a fjord, or essentially a marine valley in the Pacific Northwest, just north of Vancouver. And it shows how what we generally think of as sea level. When we think of sea level, we think of this placid, kind of bathtub-like scenario. And that's the very first thing I want to dispel today, is that is not what sea level is. Sea level is not like it is in a pool. When you think of a pool will be filled with water, and if no one's in it and you let it sit there for a while, all the water goes really still, unless of course you have a pump on, but it goes really still. If you were to actually put a tide gauge on one end of the pool and a tide gauge on the other end of the pool, you would measure the exact same level of, quote, swimming pool level at that moment in time. And then only when people jump in, you get some waves and so forth, and we can have to average those out to get rid of some of that noise. But the problem is the ocean doesn't work like a pool. First of all, we're not in a swimming pool. We are on a spherical Earth. And the level of sea, of course, varies dramatically, both locally and globally. So this is a picture that a good colleague of mine took in the Drake Passage, which is known as the stormiest ocean in the world. This is actually a benign day here. This was on our way to Antarctica when we went to do some climate change studies in the Antarctic Peninsula in 2003. I went there as a geologist. I did not take this picture because when this picture was taken, I was in the bottom of the ship, living off water and cookies in my bed. I get seasick just looking at a rubber ducky in a bathtub. So this was hell. This is 3 days of hell right there, the Drake Passage. But he took this picture and let me use it. And it gives you an idea. If we're going to measure sea level varies on a very local scale because there's lots of waves. So if we're going to put a tide gauge onto the shoreline and we want to measure what this average height of the sea is, we have to get rid of this noise. We have to essentially filter out these waves, the ups and downs of waves and local disturbances. And of course, we all also know that we have tides. And here's a great picture of the Bay of Fundy. I love this image because this is one of the places that has one of the highest tide levels or highest tide level changes in the world, something above 10 feet. And obviously, if I had a tide gauge here on one time, half the day would be measuring a very high sea level, and half the day we'd be measuring a very low sea level. As a matter of fact, it would be dry, and it would be measuring anything. And so again, we have to filter out these variations in noise to get an idea as to what local and regional sea level actually is. So those are things that we're familiar with in general. But here's something even odder, and that is that we tend to think that the ocean is flat. That when I walk up to the ocean and it's not windy and there are no waves, and let's say there were no tides, that the ocean globally is all at the same level. After all, that's what we're measuring from, right? Sea level. And the answer is that's not true. It turns out that the ocean actually has bulges in it. There are high points, there are low points, there are various things that happen to the water levels based on their temperature, based on salinity content, based on currents, based on wind blowing across the surface that actually, quote, pile up ocean water, that in some areas of the ocean may actually be 2 or 3 meters higher, not related to tides, than it is in other parts of the ocean, simply but overstretched out over very, very long distances. And so to us, it seems like it's all flat. So it's not like a swimming pool. It's not just all flat or one flat surface. It actually varies globally. And that explains in large part why so many tide gauges around the world are measuring. We're not really so much interested in an actual number. We're interested in a trend, because the sea level in different places is different. It is not the same everywhere. Now, we define mean sea level rise as basically what we call a geoid, which is kind of a fancy term for essentially a sort of a surface that is gravitationally equal everywhere. And this is sort of an idea that is fairly well defined. And we say, okay, so this is the spheroid, so to speak, that we're going to encase the Earth with, and we're going to measure sea level from that. And it's essentially a mean sea level measurement. So the way we measure sea level has dramatically varied over time. Of course, in the early days, and we've been doing this for well over several hundred years, as long as we've had, or people have gone out in ships that have been interested in tidal forces and so forth. Hence, we actually call our tidal gauges, not so much sea level gauges, because we're interested in tides. And of course, the most simple way of measuring the tide is just having a tidal staff. And you can imagine this is pretty difficult. It's also really time intensive, because you're going to have to have somebody stand there all day long, and 5 minutes, everybody read up, and was that a wave? Or, oh, wait, now the wave, oh, no, that was a splash because the boat just went by. And so it's obviously not very accurate. And so people have given this tremendous amount of thought over the past 200 years, trying to come up with devices that essentially filter out this noise. It filters out the waves, it filters out splashing, it filters out, and then ultimately gives us the ability to average out the tides as well. And so what we see today is most widespread across the globe are acoustic sea level gauges. And what you're looking at is sort of a very simple schematic here. We've got this acoustic generator, which basically sends sound down a tube. And that tube has holes at the very bottom, so the sea can actually move up and down. Notice that the water inside the tube is actually, quote, still. This is also known as a still well. And it seeks to remove some of the wave or the background noise created by the waves. And so what this acoustic sensor essentially does is measure the ups and downs of sea level, and it spits out a data logger there. And this is how the sea level is measured today, at least using tidal gauges. Where lots of different tide gauges are still active that do this in different ways, but this is a cheap and fairly reliable way of doing it. So we actually have several tide gauges off the coast of North Carolina. So, and here they are. These are our major tide gauges. Not all of these are active because some of them actually have been destroyed by hurricanes, but we do have historical data from them that we use to look at current day situations as well as make future predictions. So when I talk about tidal forces and I talk about sea level rise, these are the sites that are projecting or giving us this data. And here it is. So these are mean sea level rise rates for these tide gauges. And the first thing you should notice is that they're clearly all very different. As a matter of fact, if I put them next to each other, there they are. And one might look at this and say, ha, see, tide gauges, the sea is as flat as an ocean, it's flat as a glass plate. Obviously, they should all be the same, because that's the case. And so sea level rise cannot be measured. Well, that's false, because the ocean is not, as I said earlier, a flat sheet of glass. It is not like a swimming pool. There are local variations. But what we are generally interested in is the general trend. And the general trend is also not the same here, clearly, because some areas actually the sea is rising faster, and in some areas the sea is rising slower. And that may not make intuitive sense to us, but again, this is because of local currents, this is because of local wind conditions, because the ocean being piled up against the shore. There's lots of small little variables that go into this we have to take into consideration. And then also, as a geologist, very importantly, is that not only is the ocean rising, but in some places the land itself relative to the ocean is either rising or also falling. And so that's actually also recorded by the tide gauges, right? But in some ways it really makes no difference, because if you live along any one of these coastal areas, it doesn't matter whether or not your sea level is rising because of global warming or whether or not your sea level is rising more because your land is subsiding, because in the end, sea is still rising. Because in the end, if you're living there, whether or not your island is going under because of some sort of subsidence issue, because of geological forces, rather than some sort of increase in the volume of the ocean, in the end, it's all the same. So what we really have to look at is just in general what the sea level rise is. So on average in North Carolina, it's around 2.88 millimeters, at least based on this data that I'm showing you here. It's around 2.89 millimeters per year. Now, let's compare that to a global mean sea level curve. So these are well over 188 tide gauges that are all across the globe. And they're all measuring essentially sea level in different places. And then they have averaged out. And we're basically we're looking at this all the way up to 2010. And you can see there's clearly an upwards trend. But what's really interesting here is that the global upwards trend actually here is smaller than it is in North Carolina. So that tells us various different things about North Carolina geology. It tells us something that about our tide gauges probably are influenced by local factors as well. But again, it makes no difference, because the sea level rise we're experiencing in North Carolina is real to us, because that's what our coast is actually experiencing. But the tide gauges here show around a 1.7 plus or minus 0.2 millimeters per year increase over or since 1860 there. Now, it turns out that since the 70s, we've also been doing, since the early 1990s, I'm sorry, we've been doing satellite measurements of sea level rise. And here's why this is a vast improvement. Remember, a tide gauge is sitting on the shore, or it is sitting on the shoreline of an island, per se, and that's the tide gauges. Tide gauges, essentially, in the world are measuring what the ocean is doing along the shoreline. It's not paying any attention to what sea level is doing in the open ocean. These guys can do this. So these satellites essentially have been measuring global sea level rise, or global sea level, since 1993. And they actually, this is their data overlapping here, and they come up with a global sea level rise of about 3.2 plus or minus 0.4 millimeters per year between 1993 and 2013, which is almost twice as much as what the tide gauges are measuring. And one might say, well, this means the satellites are wrong, or it means the tide gauges are wrong, or they're both wrong. Well, they could both equally be right. Because the thing is that these are measuring vast amounts of ocean, or coverage of the ocean that the tide gauges are not picking up. So they're covering the open ocean as well as end fluctuations in the open ocean, as well as what the tide gauges are picking up. So these numbers are not canceling each other out just because they're different, and they don't tell us anything about the accuracy of the measurements, or imply anything by that neither tide gauges nor satellites can measure sea level accurately because they, quote, contradict each other. They do not. They're complementary because they're actually measuring different things in some ways. And the satellites probably are more accurate in their global assessment of what the overall global ocean is doing. So if we wanted to do some projections, because we're interested in what might happen to our coastlines, let's say over the next 100 years, one of the place to start here, and what I'm showing you, by the way, here is that blue curve is the global tidal gauge curve, and the little red line there is the satellite record projected on top of that. And I apologize ahead of time. I'm using centimeters, and wherever appropriate, I'm also going to use inches, just to warn you ahead of time. But basically, what we could do is we could project what we know from our tide gauges and what we know from our satellite data into the future and see where sea level might be. And that's what exactly we're going to do here. So we're going to use, first of all, just our North Carolina tide gauges. Let's just be curious about where would it be if the current rate of sea level rise continues the way it has been based on our North Carolina tidal gauge records, some of which go back to the 60s and 50s. And that's where it goes, right there. We're talking about 20 centimeters or so, and I should say that the numbers here are moving up and down a little bit, plus or minus a few inches, because it turns out that when you make sea level rise projections, some of them are made from a 1990 baseline, some are made from a 2000 baseline, some are made by a decadal baseline, so these vary a little bit, but it really gets lost in the resolution of the graphic anyway, so it makes very little difference there. So that's essentially where we could expect to be by 2100 if just sea level has been rising the same rate that it has been based on North Carolina tidal gauges. Now, if we look at global measurements, the global satellite average, actually the tide gauges are lower, give us about 6 inches globally. And if we look at the satellite measurement, then we have about 11 inches. So somewhere between 6 and 11 inches is what we can expect by 2100 the sea might rise if it continues to rise at the current rate. And of course, that is where the crux of the matter lies, because we understand quite a bit about what causes the sea to rise. And an understanding of that is crucial, because if any one of these variables changes in the future, so will our rate of sea level. So let's take a look here. This is a very simple schematic of an ocean basin. Okay, very simple, just to give you an idea as to sort of all the different things that people take into consideration. We got some mountains on the right there. We got our seafloor spreading ridge. Our global ocean, our land surface looks something out of Minecraft. Right? It's got a very low resolution there, but just for simplicity's sake. So how are we going to change that sea level? Well, we're going to have to take water out of it, the ocean, or we're going to have to put water in it is one of the major ways to do it. And especially on short-term levels, or short-term like several hundred years scales. Overall, the global ocean it can have sea level drive dramatically change by just having the seafloor spreading ridge rates increase or decrease. But we're talking on the scale of eons here, so nothing of this nature is going on today or is affecting us on such a small time scale. So one of the interesting ways, I think, to look at this is how much water do we have on land or elsewhere other than the ocean that we could put into the ocean to make sea level go up or make sea level go down. And if you go to the United States Geological Survey, they have had, this is work that was done years ago, well before we ever really even worried about climate change, and these numbers have been cranked out over and over and over again, essentially, is that 96.5% of the world's water is found in our oceans. So most of the water is already there. That's not that surprising. 3.5% of water is what I call other. That water is water that we could add to the oceans to cause sea level to rise. So let's take a look at what that water actually is. If you take that small 3.5%, and we're going to split that now, what actually makes up that 3.5%? It turns out that almost half of it is glacial ice, and the other half almost is all groundwater. And then there's this tiny little sliver up there, and that tiny little sliver of water is what we know as, well, moisture in the soil globally, permafrost, lakes, the atmosphere, and by lakes I also mean rivers and so forth, swamps, rivers, and then last but not least, you. Watermelons. No, I mean organisms. Okay? And so it turns out that there really are only two major reservoirs of water that we have in order to significantly change or add to the ocean volume over short periods of time, and that is groundwater and glacial ice. So how does that happen? Well, let's go back to our little schematic here. Here, what I'm having there, that's not just a white block. That's supposed to be glacial ice sitting on land. And as the air temperature of the planet is warming, so does the melting rate of the ice increase as well. And so as ice melts, of course, it's going to melt, and it's going to add water to the ocean. And we know from the geological record, or what I like to call the fossil record, that this can happen at various rates. And it definitely can happen on a 100-year or centennial or millennial scale, very fast even on decadal scales where we can have measurable differences. So by reducing the ice cover, we can increase sea level. The other one would be, let's take all the groundwater out of the world's ground somewhere for irrigation purposes, put them on our land and let it just run off right into the ocean. Instead of going back into the groundwater table, let's just drain it back into the ocean, and that would be another way to see or to make sea level higher. So people, not surprisingly, have studied this at great level, trying to figure out which of these is primarily important or which of these is primarily adding to the world's oceans at the current moment, and the answer is neither. Because actually the most important contributor to sea level rise over the 20th century has not been ice, and it has not been groundwater. As a matter of fact, groundwater plays absolutely no role and probably has not played a role until probably maybe in the late 1990s. And whether or not it is playing an important role right now is still up for debate and discussion. There's some data out that suggests that perhaps, yes, we are adding a few millimeters now per century because of groundwater extraction, but that's fairly new science that the scientific community still needs to validate. But it turns out the number one cause of sea level rise isn't because we're adding water to the ocean or because glaciers are melting. It's because the oceans are becoming warmer, because the air temperature is becoming warmer, and the oceans act as a huge reservoir of heat. They absorb heat into the ocean, and when you warm up ocean water, or particular water or anything, it actually increases, so to speak. That is, its volume begins to change. And so it essentially expands. And we call this thermospheric sea level change. And that is actually where most of the sea level change that we've seen over the last 100 years, we believe, comes from thermospheric change. It is not because we're seeing massive ice loss yet, but because we're just seeing massive temperature increases, and these temperature increases are resulting in a warmer ocean. So of the three major components then, glacial melt rate and groundwater use currently, at least in the 20th century, have not played much of a role. Thermal expansion has played a very important role in raising our sea levels. So we might ask, how is global warming going to affect all three of these? Well, one of these is kind of irrelevant to that question. At least we don't really know how relevant it might become, and that's groundwater use, because that's a human decision. How are we going to use groundwater? How much are we going to recycle? How much are we going to let run off? That's controllable by us. But when it comes to glacial melt rate and thermal expansion, essentially that is going to be ruled by how warm the atmosphere might become. And so, not surprisingly, when scientists look at sea level rise, they do not limit themselves to what I call the business as usual view, which is that we just make linear projections. Because if there's anything we've learned from geology in the past 200 years, is that our planet changes. And that sea level rise has gone up and has gone down and is always changing. Change is imminent, and what we're experiencing right now, we find ourselves in a unique position, maybe perhaps, in human history where we're anticipating dramatic changes over the next 100 years in our climate. So what people then have tried to do is try to make projections about, based on estimates of how much our climate might change and where might this lead us to sea level rise-wise. So I'm going to give you a couple of different authors here who have studied this. And by the way, these are not all, this is a global sea level rise community. Most of these people have never been to North Carolina, or some of them, okay? They don't care about local politics. They don't care about American politics. They are on a global scale scientist, and when they're doing their science, they're not thinking about what we or our particular policies are. So these are projections based on models. And one of the first things you can notice there, of course, is that there's quite a bit of variation. That's because these models are doing various different things. These are not all the same models. These are what we call semi-empirical models. That is, they're actually trying to use a proxy or some sort of measurement in the past, some sort of relationship between something that we know happened in the past and something in our measurements of sea level rise. So for example, some of these models try to connect sea level rise with temperature rise. What is the relationship over the last 100 years or the last 150 years between the temperature that we've seen rising and the amount of sea level rise that went along with that? And then what we use is we plug this into models that are by the Intergovernmental Panel on Climate Change, is widely used across the globe to model climate. And these models essentially make estimates about how much coal are we going to be burning, how much petroleum, maybe whether or not we're going to have more gases in the atmosphere than today, or less, or fewer, whether or not our emissions are going to change. So there's actually economic models, and they make projections. And they then put this in and saying, okay, well, let's assume that by 2100 at our current rate, we're going to increase or double or we're going to increase our rate of greenhouse gases. Our planet is going to warm at a certain point. Where would that sea level take us? And that's what several of these lines to actually show you. The blue line is very interesting. That's Pfeffer et al. 2008. And that's not really a projection. That tells us kind of what they think is possible. What they have looked at there is they have looked at and this is primarily based on ice mass calculations. They have looked at particular Greenland in this case, and they said, okay, so how fast would Greenland have to melt and lose water in order for us to reach 2 meters of sea level or 80 centimeters of sea level rise? Is this even possible? And what they did is, you can kind of imagine this. Imagine you have a room that has no door but just windows in it, and in it is a giant block of ice, and now you heat the room. And at first, you're just going to have water kind of trickle out the windows a little bit, right? Well, you want to ask the question of, what is the maximum amount of water that can flow through that window if I really crank up the heat? Like, how fast can that block flow out of that house? Well, that's exactly what's happening in Greenland. Greenland is a big ice sheet, but it's got, quote, gateways. That's the glaciers that are flowing off the ice sheet into the ocean. And what they've done is they looked at the gateways, that is the rates of flow of all these glaciers, and asked, what is a possible range at which that these glaciers could actually flow or melt based on what we're seeing them today. And that puts sea level rise projections by 2100 to about 80 centimeters. And what is the absolute max possible that, in other words, when the water is just coming out of there, like there's basically the maximum possible would be about 2 meters. And so they think based on just Greenland alone, they're not even considering the Antarctic ice sheet here, because we're not sure whether or not the Antarctic ice sheet is going to play a great role or not in sea level rise calculations anytime in the future. But so this is basically sort of a what if or what is possible projection. If you look at all of these, and I want to point out one more, the Grinstead et al. 2010, what they've done is they've looked at 2,000 years of temperature records, and they've looked at both geological as well as measurements of tidal gauges, estimates of sea level rise, and they come up with 2 different models, and the one model on the left there that is brown that goes all the way up above 2 meters is considered a high scenario, which is very unlikely. What's interesting is I'm showing you the full range of all the scenarios run. When you ask or you read the papers, which I can provide you with, what's interesting is they will tell you is that they will essentially usually break up their ranges into unlikely or likely and certainty kind of probability estimates. And it turns out that if you look at these one by one, the sort of overall range of estimates falls that by taking into consideration ice loss, and that ice loss will increase with warming, and that warming will also increase thermospheric sea level rise, and not even really looking at Antarctica yet, is that we could have as little as 6 inches, but we could have also as much as perhaps 80 inches of sea level rise, which is really unlikely, but it is not impossible. Okay? So if you look at the projections and you look at the consensus that's forming, ooh, there's a big word, consensus among sea level rise scientists is that we don't really know what the upper limit could be. What we think is that we're probably underestimating it currently. We don't really know for sure what the lower limit might be, but we all agree that it's going to be higher than just a linear projection. We just don't quite know yet by how much. But the consensus is that based on our best science, our best estimates of future change, our best models, our best understanding of ice sheet behavior, our best understanding about how climate responds to temperature increases, is that we're probably going to see, it's very likely we're going to see about 3 feet of sea level rise by 2100, which is around 36, 39 inches. And that is where currently, as we know it, the consensus lies, is that we ought to be preparing, in however shape or form, by 2100 we may be experiencing 39 inches of sea level or 36 inches of sea level rise, perhaps. And that's what the models, that's where the greatest overlap of these models essentially happens, somewhere between 80 centimeters and a meter, right there. So people ask me, is this true? And has this been proven? Well, it depends on your terminology of what truth is and what proof means. I actually tell my students never to use the word proof in science, because there's no such thing. Let's leave proof in mathematics. There are certainty ranges, and there's justification. Are we justified, based on the best available science today, to say that by 2100 we would very well likely have 3 feet? The answer is absolutely yes. Will it happen? Likely. What does likely mean? I'll leave you up to think about that. But the problem is that science cannot always provide black and white answers when people really want to have black and white answers. We can merely give you some ranges based on the best available science, so that we're justified in making these kinds of projections or conclusions. And then it's up to the policymakers to think about how they're going to apply these. For example, if tomorrow you decided to build a nuclear power plant, which would very unlikely to happen in North Carolina, knock on wood, right on the beach, right, that wouldn't be a very wise decision, because that power plant is designed to last perhaps 100 years. Because in 100 years from now, it might be threatened by rising sea level. But you're going to make very different decisions for the small homeowner who's going to maybe be living at the shore, who can move their house, who may not even live there 50 years from now, right? So there's going to be very, very different scenarios people are going to play out in their head when it comes to policy making. To make a policy today as if 39 inches or 36, 39 inches of sea level rise exists today is ludicrous, in my personal opinion, because it's not coming tomorrow. It's coming in 100 years. But the other thing that is also ludicrous is to say and to ignore it, and that would also not be very wise. So this is something to kind of play around with a little bit. This is the Google Maps sea level rise application provided by NASA with NASA data, and what it shows you is what parts of the coastal plain of North Carolina would be ultimately not necessarily flooded, but essentially would be driven to erode rather rapidly because of sea level rise, depending on how many meters sea level rises there. And so you look at the browner parts, and you can see that significant parts of the North Carolina, especially in the northeastern part, is affected by this. All right. So this is actually just an elevation model, and they're projecting the sea level rise on it. It turns out that the amount of erosion that's going to happen is not shown on this. So it could actually be dramatically bigger than what you're seeing there, given that we're not changing anything in our way our coastal policies are made or the way our coast is armed and so forth. So for those of you who want to delve deeper into this, one of the really fascinating things, of course, is the North Carolina Sea Level Rise Report from 2010. And then in 2012, if you want something a little bit more up-to-date, this was a great read. NOAA came out with a global sea level rise scenario for the United States National Climate Assessment. And I find this to be an excellent read. Whoever wrote this should get an award for writing science for the public in a relatively understandable language. I thought it was really good. That gives you much more background on all these models and what they did and what they can tell us and what they cannot tell us. So these are some very good resources. They're available for free online. And then if you're interested in the climate debate in general, or interested in what climate may or may not do to North Carolina in the next 100 years, and you want to get involved, the North Carolina Citizens for Science is a brand new group of citizens who've come together to essentially, our goal is that whatever our policy is, it is based on good science and consensus science. And so this is one way to get a hold of us. And then last but not least, here are some recommendations I can make for some websites that provide some excellent information about sea level rise, about global warming, and the science behind it. Here are some books for reading that are really good. And then let's see here. I guess that's it. Yeah. Thank you.
So any questions for Alex?
Alex, Jim Wheeler, a question about the impact that air pressure has on sea level locally. Is it minimal?
It depends. On a short-term level, it can be dramatic because that's what essentially a hurricane does, right? So a hurricane, the air pressure essentially creates a storm surge. It's almost like having a vacuum cleaner that's sucking up the water level. Now, on a short-term level, you're going to push that water up, and then when the storm comes on land, it essentially brings that water with it. That's why when there's a hurricane, you get a storm surge. On a long-term level, it's something that essentially gets averaged out on the tide gauge level. It does show locally, there could be whatever the climatic situations are locally or whatever that average is, but it's minimal.
We in Onslow County have some shoreline, and listening to you telling me that you're going to have some 3-foot sea level rise, we here in Onslow County also have more than 20 sinkholes. How would the sea level rise impact that?
That's a very good question, actually. Thanks for raising that, because there is a, let me use Florida as an example. Florida is in trouble of all the states because it's obviously very low sea level. And so Florida is very concerned about how they're going to, quote, armor their shorelines. How are they going to keep the ocean essentially from getting their state to go underwater? And there's a lot of talk about, well, we'll just raise the levees, or we'll build a very sort of system that essentially keeps the water at bay. The problem is that the rocks underneath Florida is essentially like a Swiss cheese. And so even though you may build large walls around all of Florida and keep the sea out, it turns out that there are pools and lakes in the middle of Florida that actually have tidal ranges, even though they're hundreds of kilometers away from the ocean. That's because under the rocks, they're connected to the ocean. If the sea level rises 3 feet, that lake is probably also going to rise. Maybe not 3 feet, but enough to actually spill over inside your levee protected area. So the problem is that essentially you can't really armor shorelines, at least in Florida, to protect against sea level rise, because the bedrock essentially all the way to the interior of the country is connected to the ocean. If you raise the ocean, so does the bedrock water inside the state. So as for North Carolina, that's something that we would have to consider here as well, is that again, our bedrock geology is quite different, although our bedrock geology is not that dramatically better, because we have the vast coastal plain sediments, and they're fairly, depending on what you're in, they're fairly permeable. And so yeah, you're going to get groundwater being pushed up. You're going to see the freshwater lens being pushed up as sea level rise essentially pushes it further and up. And you're going to probably see, as to exactly what kind of changes you're going to see in sinkhole development, I couldn't tell you. It's usually more of a localized phenomenon anyway, based on the local geology. But
the question really, and you answered it pretty well.
But not well enough. Is that
I'm presuming, based on your prognostications, I'm presuming that as sea level rises, there's a greater possibility for saltwater invasion.
Absolutely, yes.
And we have sinkholes that will allow that, and quarries that permeate that. Yeah.
Yes, yes. I don't know if this has actually been studied in detail, or if anyone has actually assessed that risk. I know they definitely have in Florida. It's incredible whenever I have family in Florida, I ever drive to Florida, how many billboards say, "Got a sinkhole? Call me." It's a law firm. We'll probably see more of that.
How would that impact the saltwater invasion by sea level? How would sea level rise impact the saltwater
Well, the
invasion?
freshwater lens, where the ocean comes together, essentially along the shoreline, is you have a freshwater lens, and this, like for example, our Berry Islands are a great example of this. You can actually dig a hole into the middle of Shackleford Island, and you'll actually have a freshwater lens sitting on top of it. And that's because the freshwater lens is less dense than the ocean water, and so it kind of floats on top of. The island at some depth is going to be soaked through with ocean water on both sides, of course, because it's surrounded by the ocean, but you have a freshwater lens on top of it. If you were to raise sea level, then that freshwater lens would also be pushed up. And what we're actually seeing is, and some people think this is the earliest signs, or very dramatic signs perhaps, earliest signs of sea level rise, is that in trees who have deep roots, they put their roots into the freshwater lens. But if you raise sea level, even well before those trees themselves ever see any seawater, their roots are going to start dangling into salt water in the ground, maybe 6-10 feet down. And then the trees ended up dying. And we're starting to see that phenomenon around the East Coast, not just in North Carolina, where coastal trees or forests who have been around for hundreds of years are dying, and their roots are sitting in saltwater lenses. And it doesn't take much. You know, it takes, if the root is here and it rises a few centimeters, that tree doesn't do so hot. Yeah.
Can I take it one step further, being the stormwater manager? If we're raising freshwater lens and for development in and around a municipality, you have stormwater rules and regulations. And the EPA and the state wants a separation between the bottom of a BMP, most of them, and your seasonal high water table. Is it going to affect the seasonal high water table and therefore change our stormwater rules and regs?
At 3 feet, it certainly would, yes.
Okay.
I mean, that's, you know, you're adding...
Job security, just saying.
You know, the multi-million-dollar question is, at what point, you know, are we talking 2030, 2040, 2050, 2060? At what point does it become, quote, painful? And that's a multi-million-dollar question. That's not something the models can say, you know, with great accuracy. They can only give us a probability about where we might be, which is a real pain for policymakers, I might add.
The other issue from stormwater side of things is that when it rains, it's all gravity fed. So unless you have pumps that are pumping the water into the estuaries or the rivers, it's just going to flow by gravity. So if you raise the sea level, the water doesn't flow as quickly. They're already seeing issues with that in Charleston, where when they have storms come through, the water just doesn't drain into the ocean as quickly. And so they have more standing water, and the issues that come with standing water when it rains now, because there's just not as much of a pressure differential, there's not as much gravity pulling it down to sea level.
Thank you. Anybody else?
You guys are scientists, but most of the time I listen from the political world. There's a lot of denial by some of the leading people in Congress about climate change. What is your opinion about that? And what, as scientists, you should be doing?
So I tell you what, I'll give you the answer that I usually give. So I am, for the last 25 years, I have, and I don't know why, it's just a hobby of mine. Some people like to watch baseball, and I study pseudoscientific movements. I don't know why. It's just a fascination of mine. So I've been dealing with what I call denialism, not just of global climate change, but various other scientific findings for 2 decades almost now, since I came out of high school. It gives you an idea how old I am. And I'll tell you how I see it. I'm not. My opinion is one thing, but I can look at it as a litmus test. And the litmus test is this: is that by looking at what individuals that deny climate change or deny other science consensuses or consensi, whatever you want to call it, it is in some ways a reflection of how well we are doing as a scientific community to educate people. And we're doing an atrocious job at that. I'm the first one to say it. Now, am I saying that the blame for all this is to be laid at the lack of education that the scientific community is providing? Absolutely not. And there is really no straightforward answer to this. There are multiple reasons for why people deny the scientific consensus, not just on climate change, but things like an evolution and, you know, connection between autism and vaccinations and things like this. There's no one Band-Aid to it all, essentially. You know, you have to meet people where they are and talk to them. We are, I think, at a very, very dangerous point in our society where, thanks to the internet, it takes nothing for anyone to go on the internet and make a very good-looking website with lots of what I call sort of, you know, lots of math jargon, lots of science jargon thrown at you, lots of statistics that only 30% of the population, if less, can actually understand because they have never taken a statistics class, and it includes me, and it looks really good, and there's absolutely no oversight. And that's good because it's called freedom of speech, but it brings with it the responsibility of every citizen to figure out what's good science and what's bad science. And unfortunately, that may be a good idea on paper, and I'm not the first one to say it, but it is essentially impossible. because we're not all scientists. We're not, even within the scientific community, we are extremely well. We have to be extremely specialized and extremely well educated within our particular fields. It is very difficult. I have no easy answer for you. So I am strongly hoping that increased education, and obviously the thing about climate change is it's going to become more and more obvious over time. I'm afraid that by the time it becomes obvious, it is too late.
Ryan, do you want to comment on that as well? If I could ask you to join Alex at the podium. Thank you.
I like to use my waistline as an example. I know that it's not healthy for me to eat the way I do and not exercise, and yet I still do it. But that's because there's a wealth of scientific evidence that is over the past 30 plus years that has told me repeatedly, when I go to my doctor, you need to lose weight and exercise more. And that's because there are big impacts to me. And it's easier when I'm young to say, oh, those are health issues I don't have to deal with for a while. I'm going to have that, extra cookout milkshake or whatever with 400 calories that it has.
Yes.
So when there are things that we've always had as a society, it's easy to put off tough decisions that have implications for us. It's tougher for us to really plan long term. And most of us don't have to make long-term decisions. You have to make them a few times. Okay, I'm going to buy a house. I may be here for 30 years. I'm going to make a good choice. But a lot of our decisions aren't really impacted by climate change timescales. But there are people who are responsible for planning long term. Hopefully they live up to those responsibilities. But it's really easy when there may be costs involved, there may be winners, and there's going to be losers, to figure out, sometimes it's easier just to say, oh, well, I'm going to ignore that. Or I don't believe it enough, so that's my excuse for not actually saying it's real. But some things are made over short-term timescales. The example I think of is they're getting ready to do a replacement for Bonner Bridge sometime in the next, hopefully, decade. It'll be done probably before then. Okay, if you're going to build a new bridge over Oregon Inlet, that's something that's going to be there for 100 years. That's something you probably want to think about climate change. You want to ask that question. What are the climate impacts going to be? I'm going to plan for a wildlife preserve in this area. I might want to be thinking about how I manage that for climate change over the next 100 years. But what crop am I going to put in the ground next season? Climate change doesn't really affect that. If I'm going to put in new water and sewer infrastructure that's going to be there for 100 years, I might want to think about those types of decisions over the long term. But for so many of us, it's so easy to say, oh, that's another election cycle. Or that'll be after I solve this next immediate problem. So it's easy to put those things off. And I think, as Alex said, well, at some point we're going to come back and say, gosh, I wish I had made a better choice back then when I had the information I needed and had not procrastinated. But we all procrastinate as humans, and in some sense that's what we're just doing as a society now. There's lots of reasons for it. There have been discussions as to whether it connects to our fundamental belief systems or whether it connects to our views on religion. There's all these other things. I don't know a whole lot about those things, but I know it's really easy for me to procrastinate and put off making good decisions. I figure the rest of us are probably like that too.
Wait, Ryan, you touched on if we were building a bridge or if we were a municipality doing water and sewer. Let's take it one more step down. What if you're an individual homeowner? What kind of things should you be thinking about if you're 20 versus, 50? Kind of decisions should you be making based on this type of data?
Okay, so let's pick someone who's going to be a new homeowner. And they're going to hopefully buy a place and they're going to live there for a long time. Right now, you have to know if you're living in the flood zone, the floodplain. It's usually the 100-year floodplain. 50 years from now, when you're retiring in that house, that floodplain is going to look a little different. So you may want to think about, how close am I to the floodplain? Am I right on the edge of it now, where I could build legally and not have to have flood insurance? Because in 40 or 50 years, that you may need flood insurance for that. And maybe you want to look at higher ground. The water table that you rely on now for your fresh water supply, where does that come from? Is that going to be connected into some of this? Is it on a municipal system or is it on a private well? Those kinds of things you probably want to, you can always change over in the future, but if you're going to invest in that now, you might want to think about that. There are probably other examples that I can't think of right now, but those are two that come to my mind. Alex, you probably have better.
That's great, yeah.
Any other questions from the audience? Well, Alex and Ryan, we'd like to thank you. I'm going to hand the mic over or ask Diana to step up. She's going to do the closing remarks for today's presentation. You're solo.
I do want to thank both Alex and Ryan for coming down here today. This is a special presentation of the New River Roundtable, which does meet monthly. Our next meeting is going to be on October 17th, meeting at Sturgeon City. So if anybody out in the general public would like to come and visit that meeting and see what we do there, please do that. If there are any special kinds of topics that people are interested in that you might like to have a presentation brought to you on, annually we do the State of the River Forum. That's usually in the spring, and you've probably been seeing those presentations on G10 TV over the last couple of months. Again, I would like to thank Alex and Ryan for being here today, and to my co-hosts for this event. Thank you very much.